Okay. I just sent you. What is this? Thermodynamics?
Yep, we're doing thermo. Okay, I guess it's officially time to start. Oh no, you're not yet at the minutes yet. I'm giving your test back. Okay. So you get your test back. I'll post the test. And I'm recording. I just say disclaimer, of course. Do you guys like it when I post the lectures? Is that a good thing or okay?
I haven't watched one of them yet.
Okay.
I think they could be useful. I mean, I kind of read the textbook, that's all.
You think they could be useful?
I think they could definitely be useful. I just read the textbook and do examples, so
Yeah.
I usually don't look back at them.
But did you guys like that I spaced the questions out more this time? That was okay. That was another suggestion that I got in the survey. That's a good.
Like the review?
The what?
When you were recording the review?
Yeah. What about it?
That helped a lot.
Oh, okay. Yeah. The first time or the second time?
Second time.
Okay. Yeah. Okay. I gotcha. So okay. Anybody have any questions about anything before we start, or anything you want to talk about? I'll post the midterm, the blank one online. So, do you have something?
Yeah, can you tell us about the final? I saw on the syllabus it said 70 questions.
Yeah.
1 through 17 and 21.
It's 70 questions, and it's comprehensive, yeah. But I mean, like,
Is there a curve on it?
yes, it's a pretty big curve,
Okay, that makes sense.
and it goes by percentile. So it's a standardized test. So there's a percentile, and it's it's 50. If you get a 50 percentile, you get a B in the class, and it's like it's not even getting half of them right. I mean, it's less than half. Yeah. So
And then it's chapters 1 through 17 and 21.
yeah, nuclear chem. There's only a few questions on nuclear chem.
And that's the chem 1, the 161.
Oh no, nuclear chem. We'll get there at the end. It's just there's like I think it's only 2 questions. It's like one is balancing a nuclear equation, which is easy. It's just the top numbers and the bottom numbers are the same. And then the next one is like sources of radiation or something like that.
And that's like chapter 21.
Yeah, which we'll only cover in like 1 or maybe 2 lectures, probably only 1. But it's comprehensive because you do have to do things like calculate molar mass, which is technically covered in 161. So that's why I put chapters all the way. Yeah. So we can talk. We'll talk about it again as we get closer. The questions are easier. These questions are harder. The ones that I have in these midterms, and the other thing is that there's only 4 choices on the final. So these have 5, right? So it's 4 choices instead of 5. Easier, no guessing penalty. And there's no guessing penalty here either. So
And it's 2 hours.
I'll give you as long as you want.
Nice.
So we'll sort. The only thing is that that's a conversation we're gonna have to have later because of I want to figure out if it's going to conflict with any of your other. I'll do it in my time block, but I can come before and stay after. But I mean, some people are going to have other classes that may conflict with that. And you can always go to the testing center. Testing center option is open at any time, but the testing center is usually crowded during finals week. So that's the other thing about it. And sometimes people want to take it early too. If you want to take it early, that's fine as well, because sometimes people want to like leave for trips and stuff. So, but I'm flexible in that. Well, as far as me proctoring, I only want to do it once. So if the date doesn't work, it's going to be in the testing center. So, just because I don't want to sit there for 3 hours.
Sure.
So, but other questions or? No. Okay, so we're we're moving on and talking about thermodynamics, and here is a artistic. So I guess it's hard to see here, but you have this machine that the water is flowing uphill and then turning a machine, and then at the top it says heat tax. At the right it says free energy. And it says perpetual motion. So essentially, though, this is one of those optical illusions. You can't make this machine. This machine does not exist. It will never exist. And perpetual motion, at least in a macroscopic sense, is impossible. So you can have perpetual motion at a molecular level. So at absolute zero is no translational motion, but like a water molecule at absolute zero will still rotate and vibrate. So you could say that's perpetual motion, but not motion like your car running forever without anything. And this comes to something we refer to as the heat tax, and it means you cannot break even. And the reason is that because of entropy. We'll talk a little bit more about entropy today. So today is going to be a lot of talk about entropy, and then on Wednesday as well. So to illustrate the heat tax, let's talk about how we generate electricity. So almost how most of the way that electricity is made is by turning a steam turbine. So the way that we get electricity, most electricity here on Maui from this. There's other ways you can do it. You can use a turbine. That's what the windmills do, and hydroelectric do that. Also, your car's alternator works in the same fashion. That's using a turbine to run a generator. Photovoltaic gets electricity directly from photons, but this is how the vast majority of electricity is generated in at least the United States, if not the world. The United States, it's on the order of about 90%. But what you have is you have a flame heating up water. Okay, and this apparatus is called a boiler. Boils water. Water vapor goes up and it runs a turbine, which is basically a fan, and then that connects to a gear shaft that runs a generator. So the generator, it's a wire, and you have magnets that spin around a wire, like so. And here in the United States, that wire spins at 60 times a second. In Europe, it spins at 50 times a second. So, and those magnets going around a wire, it induces a current flow along the wire, and specifically referred to as the electromotive force, the EMF. So, like when you do something, these lights don't turn off, but if you turn off the light and turn it back on, what happens is there's a signal that runs along the wire at the speed of light. So a lot of people think the electrons in the wire are moving speed of light. They're not. They're moving at about 10 to the minus 5 meters a second. So that's really, really slow. So 10 to the minus 5 meters a second, so that's 10 micrometers a second. I mean, that would take you all day to go that far. So electrons and wires on a macroscopic scale are moving very, very, very slowly. They can buzz around them around in the elements. They can move very quickly then, but not that fast. The signal is carried via photon. So the electromotive force is a photon in, photon out process. The photons are being exchanged along the electrons. Anyways, so the generator runs and it creates an electromotive force across the line. So then the generator generates electricity, and you run electricity through the high tension wires to your house, and then you turn on your stove, assuming you have a coil stove. I actually have a gas stove at home, but I used to have a coil stove. What happens in a simple electric stove heater is it's friction. You run electricity through the coil, and it's a resistor. So a resistor resists the flow, and resistors, it's friction. It's just electron-electron friction. It generates heat, and then you put your pot of soup on the burner and you boil up your soup. So the question is, what's the heat tax? Well, do we get all of the energy from the flame to the boiler? No, you don't. So some of the energy flies out from the flame via radiation, doesn't hit the boiler. Hit the boiler, does all the energy go to the water? No. The energy also conducts along, usually metal, and well, it's almost always metal. So you're going to lose energy by conduction, also radiation from the boiler itself. When the water boils, of course, you're going to lose energy to the walls. You get the turbine though, so depends on the type of process. So most electric turbines use what's called superheated steam or dry steam. And what happens is that steam comes in and steam comes out. For nuclear reactors in the United States, we use saturated steam, which means steam comes in and it condenses on the turbine. So the reason being is that we don't like to run our nuclear reactors all that hot. We keep them about 500 degrees Celsius. And a candle flame, like if you get a tea light candle, that's between 550 and 600 Celsius. So a candle flame is hotter than a nuclear reactor, at least in the United States. So nuclear power is a little different. It's not as efficient. It could be more efficient. So a nuclear power plant is about 20% heat efficient. Your car is about that too. Like an auto engine car is about 20% efficient. A boiling water plant is usually about 33% thermally efficient. So what I mean by thermally efficient is the amount of work that you get. So if you put 100 joules of heat into a boiler plant, you get about 33 joules of work out. Your car engine, when you burn gasoline, if you put 100 joules of energy into it, you get about 20 out in work. So what's that? The conversion factor is usually about 85%. For batteries, it's about 85%. So the energy that you put in, if you put in 100 joules, you get about 85 out in work. So, depending on the type of turbine you have, you're going to have energy loss from the turbine. Why? Well, because of friction along the gears. So it might wobble a little. There's lots of things that cause energy loss along the turbine. The generator, same thing with a turbine, just mechanical losses because it's a moving part and you're going to lose energy there. What about the high tension wires? Do we lose any energy in the high tension wires? Yeah, you do. One of the tricks for high tension wires is, so the energy loss is through resistance and just friction. And if you have a higher voltage and a lower current, there's less energy loss. So we'll talk a little bit about this more later. But a volt is a joule per coulomb, and an ampere is a coulomb per second, and 96 I forget I can't remember Faraday's number right now. What is Faraday's number? This is embarrassing. Oh, it should be on my sheet, isn't it? Faraday constant, 96,045 coulombs per mole of electrons. So about 100,000 coulombs is a mole of electrons. So anyway, so coulombs is a symbol of charge. So an ampere is how much charge is flowing per second. So like water, think of water flowing through a river. Okay, so instead of water, it's electrons flowing. And so the amount of water is the flow in the river. The amount of electrons flowing in your wire is the same thing as the ampere. It's the current, how much electrons are flowing. A volt is how much energy each of those electrons has. So a joule per coulomb. And so voltage times ampere, volts times amps, so it's joules per coulombs times coulomb per second. That's joules per second that means power. That's watts. A joule per second is a watt. That's power. That's not for this class. This is more for physics. I know 2 of you guys are in physics. Is there more than 2 in 272? You have 3? Okay. So I mean, this is baby stuff though. You probably covered that first day. Are you in it too, or?
No, I'm in 105 with the engineers, but we found.
Okay. Yeah. But anyways, for high tension wire, the point is though, high tension wires increasing the voltage. That's why, if you ever wondered why the high tension wires are at 100,000 volts or 10,000 volts, and your house is 115, at least here in the United States. In Europe and most other places, 220. But it's better to run at higher voltage. There's less energy loss that way. But electricity was I don't want to be careful what I say. It was kind of, at least in mass production use, was pioneered in the United States. And so we made some mistakes in other countries. We improved upon them. We just haven't improved upon them. And some of our allies keep it that way, like Japan's 115 volts, for instance. So Europe is mostly 220. China is 220. But Japan and U.S., and I think Taiwan too, is 110. But it's not that much of a difference in a house, though. Other things you do is materials. Copper wires in houses. Copper has less resistance. The element with the lowest amount of resistance is silver, but it's kind of expensive. They usually use aluminum wiring in the high tension wires, and then they just use a transformer to transfer the transformers. Don't have that much of an energy loss to them. They're pretty solid. I mean, it's on the order of high 90% transfers. I don't know the exact number, but it's not a very significant energy loss there. Okay, but then we get to the stove, and then you turn on the resistor. That your heat is your option. It's essentially, most turns to heat. But then you put your pot of soup on the heater. Does all the energy from the heater go to the pot of soup? No, it goes to the vessel itself. Some of it is radiated out, right? So you turn on the soup, you can put your hand next to it, and you can feel the heat. So you're losing energy that way. So are you really using all that energy from the flame? Is all that energy from the flame going to heat up your pot of soup? And the answer is no, because of entropy. This is called the heat tax. So the heat tax there, it's the energy losses through, and the source of this energy loss is entropy. And this is also it was a very it's a very intelligent form of mass hysteria in the 1970s. So people were upset about the heat death of the universe. So we have lots and lots of end of the world scenarios. I mean, right now we have there's global warming, there's peak phosphorus, peak oil. No one really talks about peak potassium yet. Maybe they will someday. I don't know. I'm more worried about phosphorus now, I guess. There was 2012. Remember 2012? That was there was it doesn't have to be scientific. But then
Was it still phosphorus? I never heard of that before.
Oh, you haven't?
No.
So the 3 primary plant nutrients are nitrogen, phosphorus, and potassium. And nitrogen we get from air. But we mine phosphorus, and one of the issues is that some people argue that we're past peak phosphorus, which means we can't produce as much phosphorus as we use. That's their argument. And then that goes to Malthusian catastrophe, that we won't be able to feed the population. So I mean, I've just read about it. I mean, it's just, you can see, there's there's websites that go over the end of the world, and they talk about this is 20 things why the world should end today. So, but the heat death of the universe, that was a big one in the 70s. I mean, some of them are bigger than others. I mean, 2012 was a huge one. So, one of the worst ones in history apparently was when the year 1000 came around. Remember Y2K? I don't know how old you guys are, but I was alive for that. That was a big deal. A lot of people thought that the world was going to end then. It was way worse in the year 1000. They thought, at least in Europe, they stopped doing maintenance work on bridges. The world's going to end, so might as well not fix this bridge, and kind of thing. And then the year 1000 happened, and And like whenever there's a thunderstorm, people go outside and pray and like, deliver me, Lord, kind of thing. And then it passed, and they're like, well, shucks, time to fix that bridge, kind of thing. So there's nothing in the past we've had far worse. Okay, so let's talk about electricity as well. So, and this is not necessarily on the test. What's that?
Heat death of the universe.
Heat death of I didn't explain it.
Yeah.
So the heat death, if you with this example here showing the energy leaving, the idea of the heat death of the universe is that that as heat is flowing, the universe will become more and more the energy density of the universe will become more and more dispersed, and eventually no energy will be able to be transferred, and then from that, intelligent life will cease to exist. So that's the idea of the heat death of the universe. It has now no longer been able to, it's not possible now anymore because of what we refer to as dark energy, that which is making the universe accelerate faster that we don't understand. So dark energy, so there's energy in the universe coming from we don't know where. So from that, it makes the heat death of the universe not really an issue. Now there's new problems. There's the great rip of the universe. If the universe continues to accelerate, eventually the energy in the universe will tear the space-time apart. That's known as the big rip. So. But this is also, we don't know what's going on. So we have no idea what's going on. And there was a big talk about, for a while, is the universe going to collapse back on itself? So is it expand, slow down, and then revert back to the Big Bang? And it looks like that is not going to happen because it's expanding more quickly. So some things we don't entirely understand. But okay, back to chemistry and society. This, I don't have it for Maui, but the lines here are this is for Oahu. And the light pink and then the purplish line. Light pink is winter and the purple is summer. And what is unique about Hawaii is that our peak usage is from 6 to 9 p.m. So, and the reason for that is that Hawaii does not have any industry. So, there's a couple things here with this graph, though. We have a baseline. So, Oahu has a baseline of about 600 megawatts and has a peak of around 1.1 1 to 1.1 gigawatts. So, and how the rest of the country works is like this. So you have the baseline. So baseline means that things are always on. We like having electricity on all the time because we like street lights. We like refrigeration. We like hospitals. We want the hospital to work at 3 a.m., right? So we want our street lights to work all the time. So it's important to always have electricity in the grid. It's not just charging our cell phones. So then for the most of the country, they go to work, turn on their computers, turn on their ACs, run the plant that makes cars. So Hondas and Nissan are churning out cars on their robotic lines. That uses a lot of electricity. We're making aluminum, things that use a lot of electricity. So that's the peak hours between 8 a.m. and 5 p.m. And then people go home, turn on their TVs, turn on their stoves, they go to bed. So we have the peak and then a smaller time. Oahu and is Maui as well, but I don't have the data on that. Our peak time is because we go to work and turn on our ACs and our computers. Then we go home and turn on our TVs and our ovens, and that's where this other peak comes from. It's from Wi-Fi, Netflix, and baking stuff in your oven. So, and that's an issue. Is with alternative energies. And for instance, this is the solar output on Oahu. So the peak is, of course, around noon, which makes sense, midday. And and then it trails off as you go. So, but it's not really a smooth curve. It's like depends on the cloud cover. Like today, solar power is not so great because of the rain. So, and that's an issue with alternative energy is, I mean, we have most of our electricity is generated via gas by steam turbine. So why don't we just switch to solar? Why don't we just switch to wind? So let's talk about wind energy. So this is 2008, and this is actually out of Canada, and this is the estimated power generation from 2 wind farms with a combined capacity of 2,800 megawatts. You're like, that's 3 Oahu's. That's a huge wind farm, right? So 2,800 megawatts. So, but how often per year do you get 2,800 megawatts? I remember, gosh, what's the guy's name? Pickens. Do you remember that guy Pickens when he was he was talking about energy? He says, we could have so much capacity from wind. With all the capacity from wind and natural gas, all this capacity from wind. The key word there is capacity. So the capacity that 2 wind farms can produce 2,800 megawatts, it's like 10 hours a year, right? So it's not that much. I mean, how much do they really generate? Maybe 500, maybe 300-ish. But I mean, look at how many times it hits 0. So that means you have to have a backup generator. So what wind farms do typically, if they're not attached to a boiler console, that's what we do here at Mount. We have a boiler. It runs at 280 megawatts. So the primary one, it's at 280 megawatts. It's either 280 or 360, I forget. I don't remember which one. It's 300-ish megawatts is our primary. And then we have secondary ones. We have the wind farm. We have the solar. There is another one in Hana. Hana is not connected to the Kahului grid, but Kihei, Lahaina, Upcountry, they're all, and of course Wailuku, Kahului are all connected to the same one. And wind energy is also weird because you think, oh, high wind is the best situation for wind. Well, the worst situation is low wind. The second worst is high wind. The third worst is medium wind, and the best for wind farms is low wind. Why? Because of consistency. Consistency is the best. So here's no wind. So here's what I'll put. And so no wind means that you have a boiler plant on. So, and you have peak hours, so you run less efficient processes during peak hours. So you can run a gas turbine, for instance. So a gas turbine uses natural gas, and typically they use a rotary engine. Rotary engine is just kind of like a rocket that spins around. So, and then same idea, gear shaft runs a generator. And so no wind, that's how you use it off of all fossil fuels. Medium wind, there's medium wind. You have some parts where it hits 0. High wind, and it's just a mess. Because you have 2 things that are really bad for a grid. You have surges, and you have no electricity in a high wind situation, both of which will shut a grid down. So you need to have, for really any type of wind power, you need to have a smart grid that can draw electricity from other areas. So, and it comes back to the idea of this heat loss, and this is a problem that we're trying to solve. And this is something we're trying to solve here in Hawaii. There's lots of research money going into it because, I mean, wind energy basically is not very useful because it's inconsistent. And so, how do you make it consistent? Well, some thoughts people have, like, well, why don't you use? But where wind is bad, hydroelectric is great. It's consistent. It's high energy. Why don't you use wind energy to pump water uphill and then use that to run a turbine? Well, you have lots and lots of energy loss from pumping the water, the pump, and doing all those sorts of things. There's energy losses there. Why don't you take water and crack it into hydrogen and oxygen and then burn the hydrogen? So that's a thought. It's a way to get alternative fuels. Maybe you take the hydrogen and then try to run it with cars or something else, or use the hydrogen for something else. So that's another thought. But one of the issues with hydrogen, so hydrogen is extremely explosive. It's also its energy density is low. So what do I mean by that? Like what'll get you fatter, a pound of chocolate or a pound of popcorn? Pound of chocolate. Why? There's more calories. What'll get you further? It'll be a gallon. I usually use fuel as gallons, or a liter of hydrogen, or a liter of gasoline or jet fuel. The answer is gasoline and jet fuel. They're just jam-packed full of calories. So the Air Force, they did some research on this. They're like, okay, Air Force is the single largest user of any fossil fuel in the world. The United States Air Force. Not very surprising. It's the military, and most of it is the Air Force uses the most fossil fuels, and they can have any fuel they want. And they're like, well, what's the best fuel for us to use? And they looked at it and they said, you know what? It's JP9. It's jet fuel. And they looked at hydrogen, looked at natural gas. They have to have bigger wings and shorter payloads. So the JP9 lets them have smaller wings. That's where the fuel tanks are, and the payloads can be bigger. So that's what they found out. So I mean, alternative fuels are a problem, but I mean, it is something we need to do. I mean, it's not like we're talking about peak phosphorus. We can't just keep on running oil. I mean, we're going to run out eventually. So I mean, same thing. I mean, we have lots and lots of hydrocarbon reserves, but I mean, like some estimates are 250 years for oil reserves, maybe even more. Natural gas reserves, maybe 1,000 or 2,000 years. But I mean, that doesn't mean that this is not a problem. I mean, because that 1,000 years will come by quickly. I mean, not in our lifetime, but for the sake of the cosmos, it goes very fast. Here's the wind in Oahu. You can see that it goes up and down. I looked up. So here's the wind on Maui. Where is it? Yeah, here we go. Here is the wind on Maui. At least in Kahului. This is the only one I could find with a graph. And what is the date on this? Okay, this must be yesterday. No, this must be last night and this morning. So you can see that and this is Kahului. I mean, it's actually, this is pretty good. This is fairly consistent. I mean, of course, here, and it's also this, which is night. This is nice. This is at night, right? So that when we don't really need that much electricity, anyways, and then it goes up here for peak hour. Well, I guess not for Maui. We get a lot of energy from solar, so we don't necessarily need the load then. But I mean, this is all you can see though that it jumps up and down. It's not super consistent, which is one of the problems with wind. So, and I'm sorry if I'm here. I'm like, man, Mike hates wind. I'm just using this as an example to show the challenges that we face with wind energy is because of the heat loss, the heat tax, the entropy. So, but let me move past the intro and let me talk about a little bit about. So this chapter is thermodynamics part 2. So there are some limits for thermodynamics. It tells you what the end products are. It does not tell you how quickly it will get there. So that's all kinetics, and that is something that we still do not know how to do. We can't look at something and say, this is going to happen this fast. Only by experiment can we determine that. So I don't know how many people, do you remember the De Beers commercials? I don't really watch TV anymore, but they have this diamond, a diamond is forever. Well, you never heard that before, okay.
I've heard the phrase.
Yeah. So diamonds are not forever. If you bring, at least not at this temperature and pressure, a diamond at this temperature and pressure will slowly turn into graphite. So how long will it take? Millions of years. So no, we don't really have the data on that experiment, but it's going to be very, very slowly. It's not going to happen like quickly. I mean, but like I proposed, and my wife with my with the diamond ring from my grandmother. So I mean that's 2 generations old, you know, and it'll probably survive for maybe 100 more if diamond rings are still in fashion. Although there's diamond rings from the Roman Empire. So we have diamond rings that were given all the way back then, and although they're not cut like they are today, they're uncut diamonds, but we still have them and they're diamonds. So I mean, even 2,000 years ago. So maybe in that way, diamonds are forever. I mean, because as far as human civilization is only 5,000 years old, and diamonds, well, we don't have them from Mesopotamia, but we have them from Roman Empire times. So for within a few lifetimes, at least human memories, they kind of are forever in a way. My brother, his wedding ring, he has a gold ring that's inlaid with platinum. And I told him, John, my brother's name's that ring's going to corrode because the platinum is going to cause the gold, it puts it into a circuit, and as you wear it, the platinum will corrode the gold. He's like, well, how long is it going to take? I'm like, hundreds of years. He's like, all right, no worries, kind of thing. So for that, okay. And then, so also thermodynamics can tell us about spontaneous processes and non-spontaneous processes. So, think of your friends that are spontaneous. My friends are spontaneous. They're like, oh, cool, see that waterfall? I'm gonna jump in the water. Ah! Like, hey, what are you doing tomorrow? I'm going skydiving. Let's go skydiving. You're like, man, that's not, that's too much energy. That person's very spontaneous. Like, oh, it's raining right now. I'm gonna go dance around the rain. Yay, look at me, I'm dancing in the rain. That's spontaneous. So you could say that I'm kind of non-spontaneous. Can I dance in the rain? Yes, I can, but it's gonna take a little convincing, right? Like, hey, Mike, I'll give you $100 to go dance in the rain. Then I can consider it. Same thing with processes. So iron rusting is spontaneous. It just happens. You put a hunk of iron outside in Earth's atmosphere, it's going to rust. It happens just because it's spontaneous. It happens. Can you turn rust into iron? Yes, you can. But you have to reduce it with something like carbon or aluminum or something else, and then add a bunch of heat to it. So kind of like it takes money for me to go skydiving. It'll take energy and something else, or maybe just energy. You could take iron, you could heat it up really, really hot in the absence of oxygen, and then you can take rust and heat it up really, really hot without oxygen, and it can form iron again. Or you can reduce it with something like carbon, which they do in most metallurgical metal plants and most steel mills. Or you could do the thermite reaction, put rust and aluminum powder and heat. That'll work too. So you can get non-spontaneous things to happen, but it takes energy. Also, so what about things that are endothermic? So things that are endothermic, some of these things happen, like ice melting. Ice does melt, and ice melting is endothermic. If it's absorbing energy, why is this happening? So it's in part because of entropy, but later on, the processes and reactions are also due to another thing called free energy, or specifically Gibbs free energy. So we'll talk about that a little bit more later. But most spontaneous processes, they happen because of entropy. And entropy is a probability. So it's a probability only. And this was a big deal in the 1850s as we were learning about probability. And even up through Einstein, they were still figuring it out. And it upset a lot of people because entropy is just probability. So a lot of people, most people back then, and some people today, believe in fate. So the universe was set in a direction, it's going to keep on going that direction because it was decided already. And then okay, we're going to figure out where the direction is going. Like around the 19th century, the turn of the 19th century, people thought they would solve everything. There was a lot of people who were really into physics. Like, if we understand physics, we understand where we're going, and then we know everything. We'll know who's the next president, we'll know the price of gold in 20 years, and we can infer all this because once we know which way we're going, we'll be able to figure it out. And then they figure out like, oh, well, the reason why processes happen is because of chance, by probability. And then later on, as they learn more about quantum mechanics, that there's uncertainty in things, that you can't even accurately decide what things are because of uncertainty of position and momentum and electrons and other quantum mechanical things. So that completely destroyed that hypothesis. I don't know if I call it theory. But entropy is simple probability. It's the number of ways to achieve a particular state. And there's another definition. The definition, S is entropy, is the reversible heat transfer divided by temperature. So entropy has units of joules per Kelvin. So energy per temperature is entropy. So SI units is joules per Kelvin, or Celsius, if you will. Celsius and Kelvin are the same units. Magnitude is different. Units are the same. So entropy can be calculated. Entropy is equal to the Boltzmann's constant times the natural log of the number of states. So, which means that you can have zero entropy. So natural log of 1 is 0. So entropy can be 0, which means entropy is an absolute scale. So Kelvin, for instance, Kelvin is an absolute temperature. You can have a 0. Celsius is a temperature scale, but it's a relative scale. So some units are absolute, some units are relative. So entropy is absolute. And you can calculate it out. Although it's not normally calculated out, it's usually determined by heat transfer. So let's talk more about the how it's calculated out. So let's look at two states here. So so we have two boxes, and well, I guess let me back up. Did anyone walk in the classroom today? Was anyone afraid that you would walk into a vacuum and you think, okay, I'm walking into a classroom, there's going to be a vacuum when I come in here, and my eyes are going to bulge out because all the air is in the corners of the room? Did anyone? No one had that feeling, right? Because you walk in like, you know what? When I walk in this classroom, the air is going to be evenly spread throughout this room. I don't have to worry about walking into a vacuum. So why don't you have to worry about that? So because let's make it real simple. Let's say that we have 4 gas particles and we have 2 boxes, and they can flow between the boxes. So all 4 gas particles, so they're sufficiently far apart, they don't really react, or interact, I should say. So these 4 gas particles, so they can all be in one box, or you could have 3 in this box and 1 in this box, and there's 4 opportunities that can have this. Or you can have it evenly spread, and you have 6 opportunities of this. Or you can have 1 in the first box and 3 in the other. There's 4 chances for that. And then you can have them all in the other box. So in this case, actually, it's more probable that you would have a slight, have it more in one box than the other, more likely speaking. But as you increase the numbers, the most likely state is the middle one. But if you, let's say instead of just 4 particles, what if we increase it to, I don't know, some number like 6.02 times 10 to the 23rd? What's the probability of it being all in one box? I mean, it would be 1 over 2 to the 6.02 times 10 to the 23rd power, or maybe 2 if it's in the other box. So 2 over 2 to the 6.02 times 10 to the 23rd, or 1 over 2 to the 6.02 times 10 to the 23rd minus 1. So, which means is it possible? Yes. Is it going to happen? No. Very, very, very unlikely. If you want to even like a one closer to home kind of thing, so with entropy, certain processes are random. I could take a bag of Skittles. I remember my first serious girlfriend, I like Skittles. I remember I bought a bag of Skittles, and I came home one day, and she had them in a jar, and she put all the red in the bottom, and then had the orange, and then the yellow, and then the green, and then the purple, and made auto-organized. She's like, see, I organized it. And what would happen if I took that jar and I shook it? Besides me being smacked, right? Would it randomize or would it stay ordered? Of course it would randomize. Could I take a jar? Could I take a bag of Skittles, pour it into a jar? Could I shake the jar and it all lines up? Is that possible? It's possible. How likely is it to happen? And that's like 200 Skittles, right? 200. I could be shaking the jar. It would take like 100 years or something. I'm guessing numbers, but it would take a very long time for it to even out by chance. But let's increase the number to 10 to the 23rd. There's no chance. Essentially, the most probable state is the one's going to happen. There are a few times that entropy is altered, that it seems like things happen, but for rooms, there tends to be a slightly higher concentration of heavier gases. So we're talking about xenon in the start of class. There's probably a little more xenon in the corners of the classroom than there is in the air here, because studies have shown that the heavier elements tend to accumulate there. There's been some arguments that there's been some calculations that there actually is a little bit more of a probability that would happen that way. There's some of these problems. Have you ever heard of the Brazil nut problem? Like if you have a mixed bag of nuts and you open them up, there's almost always a Brazil nut on top. And there is no clear-cut reason why. That's just one of those questions like, what is the Brazil nut problem? There's another one. It could be perception. Have you heard of the green car problem? Or the green car? Okay, so it's if you think about green cars, you will notice more green cars on the road. You're like, green cars are everywhere. It's kind of like I remember I bought a car. I bought a Honda, and like after I'm going to buy a Honda. Now I see Hondas everywhere. Does that mean that there were more Hondas before? No, it's just because I perceive it more. So there's a question: is the Brazil nut problem, is that a perception problem, or is there some science behind it? We don't know. The other thing where you have a seemingly change in entropy and nature in the ocean, there tends to be more iodine on the surface of the ocean, like the absolute surface, than there is in the bulk. So there are some changer-ups with that. Okay, so let's see here. So which one of these? Okay, which one of these changes has a positive change in entropy? So delta S change in entropy. Which one of these means that the entropy is increasing? Can you see that? It's a little fuzzy. Here, I'll draw some lines around it. Might be easier to see. Actually, I shouldn't. Is that better? Okay, it is. Actually, these boxes are connected. Oh, I guess the other thing, entropy. Entropy is also referred to as disorder. So high disorder means high entropy, or low disorder order means low entropy. So the more ordered something is, the lower the entropy. The more disordered it is, the more chaotic it is, the higher the entropy. So another example is a messy room. So a messy room is an example of high entropy. Low entropy is a clean room. A clean room has all the dirty laundry in the laundry basket. It has your socks matched. It has your t-shirts folded. It has your clothes hanging up in the closet. Okay, so everything is very ordered. What does a messy room look like? Well, the bed's unmade, which means that there's 2 pillows on the floor. The blanket is askew. There's socks everywhere. There's dirty laundry everywhere. There's t-shirts, some hanging up, some wherever. So that's the messy room is high entropy. The clean room with a made bed and socks matched and put in the drawers, though that is low entropy. That's high order. So In this case here, you have 4 particles in one box, and they're all connected, 2 in the other, and this one's empty. And here, they're all evenly spread. So the evenly spread, this is, of course, this is the highest probability. It's most likely to be this way. And this is a little less likely. You go from more order to less order or more disorder. This is a positive change in entropy. Entropy is increasing in this process. So here you have the least ordered, the most disordered, and you go to all the particles into one box. This is a very big negative change. This is more ordered. This is a negative change in entropy. And in this case, you have the middle box is the same, but you have 2 particles in each of these boxes, and then they concentrate into this one. This is an example of negative entropy. This is becoming more ordered. So this is disordered. This is more ordered. So these two are negative delta S. So entropy is lowering. It's becoming more ordered. This one here is positive delta S. This is becoming more disordered. Does this make sense? Questions with this? And most processes happen to go towards more entropy. You can go from something more random, like water vapor, to ice. So gases have the highest entropy, liquids have the second highest entropy, and solids have the lowest entropy because they're stuck in space. So you can condense gases to form solids. You can do that, but that's a negative entropy change. So you can do it, but there's always some cost. There's a caveat, and the answer is because when you cool gas down, it'll condense to form liquid or then freeze to solid. It's from the latent heat and the heat of vaporization, the heat of fusion. So the heat given off is there's enthalpy. There's heat pushing it to do it that way. It's the attraction between the molecules, and we'll cover that more later. Okay, so if you want to understand thermo is actually pretty straightforward, but the biggest problem is figuring out what your system is. So if you can figure out your system, everything else gets really easy. But we'll talk about this a little bit more as we go on. I tell you it's easy, but it's still it's hard. You have to pick the system, and which system do you pick? You pick it so the math is the easiest. And we'll go over several examples to pick that. And you pick your system, and then the surroundings are everything that's not in the system. So you pick your system. Your system is the cell phone. Everything outside of the cell phone, the sun, the planets, the next galaxy over, the classroom, it's all part of the surroundings. And like all things final, the change in entropy is the final minus the initial. And then the entropy change of the universe is the entropy change for the system and the entropy change for the surroundings. So, of course, entropy, remember I also said it's heat flow. So we really can calculate entropy is by heat flow. You're really not going to do it by using Boltzmann constant. Okay, and then we have the second law of thermodynamics. So the first law of thermodynamics is the energy conservation of energy. That's the first law of thermo. Second law of thermo is that the entropy change in the universe is always increasing. Well, it's greater than or equal to 0. Anyone want to guess when the entropy change in the universe is in fact 0? So it's when there's no heat transfer. If there's no heat transfer, then there's no change. So isothermic processes are also called, isothermic, same temperature, are also called isentropic, same entropy. And another term is adiabatic. Adiabatic means no heat transfer. So adiabatic processes have no change in entropy. And one of the equation that actually has religious implications is this equation here, is the change in entropy of the surroundings is equal to the opposite of the enthalpy change of the system over temperature. So I say this has got religious implications. This debate isn't so big anymore, but there has been, and is still in some places, the idea of intelligent design. So one of the arguments for intelligent design is that, hey, look at me. Me and my human body, I break the second law of thermodynamics. Okay, so I am extremely ordered. My proteins are all in the same way. If my sugars, my amino acids are all left-handed, my sugars are all right-handed, and I have different tissues in my teeth versus my bones versus my hands versus my liver, and they have to be exactly the same way. If you do something like, if I eat meat that has the wrong shape onto it, I will die. So the only way that I can have such an ordered person like me is if someone or something created me this way. So, but the counterpoint to this is, well, in order for me to be this ordered, I have to eat lots of sugar. I have to eat my Skittles to get that energy. And as I'm burning that sugar, so the delta H, I'm burning that sugar, I'm increasing the entropy of the surroundings. So although I am extremely ordered, I have to consume lots and lots of energy to survive and stay ordered. And if you look at the amount of entropy that I have expel through my normal cellular respiration, and you compare that to the amount of entropy loss that I get in ordering my body, then actually the entropy change in the universe, second law of thermodynamics still holds. Therefore, I can survive and not break the second law of thermodynamics. Also, evolution can happen without without violating the second law. So these are like points and counterpoints. It was interesting that I think that the intelligent design argument versus evolution actually one of the arguments was in fact thermodynamics, and the intelligent design field said, hey, what about second law? And then the counterpoint was like, oh, what about surroundings? So, okay, so this is a Jeopardy kind of trivial sort of question. I think I mentioned this. Does anybody know the third law of thermodynamics? So the third law of thermo is that a perfect crystal at 0 Kelvin has no entropy. That is the definite. A perfect crystal means all the atoms are set in space. And absolute zero, they're not moving, means that there's one state. And so a perfect crystal has one state. Absolute zero is not moving. Therefore, it's one state. Natural log of 1 is 0. That's the third law of thermo. So, but no one really uses that unless you're like on Jeopardy. It's trivial knowledge. Not useful. But okay, so what about other processes? So number of moles of gases are another way that entropy can change in chemical reactions. So if you form a combination reaction, so SO2 plus Cl2 makes SO2 Cl2 gas. So you go from 2 moles of gas to 1 mole of gas. Entropy goes down in that process. Also, if gases are evolved, so if you have calcium carbonate, limestone, and you heat it up, you can form carbon dioxide and lime. You're evolving carbon dioxide in that. Entropy increases for this process. So those are other things not necessarily included in this equation here, the surroundings. That's the change in entropy for the surroundings from the heat transfer. You can have entropy change in other places like gas evolution. Okay, so how are we doing so far? Questions? So, okay, look at this reaction here. Consider the combustion of propane gas. So propane plus 5 oxygens makes 3 carbon dioxides and 4 waters. And the heat of a reaction is minus 2044 kilojoules. So exothermic heat is leaving the system. Calculate the entropy change in the surroundings associated with this reaction. So it's negative delta H, so we have delta S surroundings, too many R's, equals minus 2044 So I'm just going to go ahead and put another 3 zeros on it. Divided by 298 Kelvin. So 25 degrees Celsius is 298 Kelvin. And don't forget the kilo. More common mistake. So 204423, 2 million joules divided by 298 Kelvin. And the sign of this, a minus is a positive, and this is a 6859, which equals 6.8. How many sig figs? Oh, we have 4. Never mind. I can leave that as is. Unless you consider 25 Celsius to be 2. I'll consider 25 Celsius to be an exact number. Joules per Kelvin. So the entropy change for this reaction is positive 6859 joules per Kelvin. Questions so far on how to do this? So determine the sign of the entropy change for the system. So since we're increasing in the number of moles of gas, this is positive. So 6 moles gas to 7 moles gas means we're getting more disordered. And then determine the sign, the entropy change for the universe. So part C, we have A, which is a positive number, plus B, that's a positive number. Can anyone think of a case when you add 2 positive numbers that you do not get a positive number? You always get a positive number. When you add 2 positive numbers, you always get a positive number. So entropy change for the universe is positive, which means, generally speaking, this will be a spontaneous process. So, questions with this one? Okay. So, we have another equation here. So reaction 2 nitrogens plus oxygen makes 2 dinitrogen monoxides. The delta H is positive 163.2. The delta S is negative delta H over T. What is the entropy change for the surroundings at 25 degrees Celsius to 98 Kelvin? So I think it's A, negative 227. I think it's B, negative 54. Okay. How about C or D? So we got 2 people playing. Is anyone stuck? Do you just need more time? Come on, guys, I need feedback. Do you need more time? Do you not get it? Raise your hand if you want me to come talk to you. Okay, you're just not playing. No one wants to play with me. I do chemistry problems. Isn't that cool? It's just like that. Don't forget the killer. Killer's the killer. That's the most common mistake here, is not multiplying by 1,000. Does anybody have any questions with this? You guys are just bored out of your minds? Okay, and this is a better place to start. So, in that case, you can have 11 minutes of your lives back. You got a lab today anyways, don't you? Okay. Or you want me to keep on talking for 10 more minutes? Lab question? Okay, I can help you with a lab question. So, in that case, I will stop. Anybody have any questions? In that case, I will stop recording. And we will end class a little early today. Okay.